One topic that a lot of people seem to enjoy in mathematics is fractals. So I thought I would show you one of the simplest fractals and then maybe take a look at some of the properties it has. So what I've drawn over here is an equilateral triangle. It's the same length on each side and it's all colored in. And so I've done this with a little marking pen so it's not colored in real smoothly, but just pretend that it's all colored in. What I want to do is go to the midpoint of each one of these sides, draw another equilateral triangle like this, and then remove the shaded area that's inside that triangle. So here's what I'm going to do. I'm just going to erase this area that's inside here as best I can. You know, it's with these marking pens, so it's not going to be perfect, but you're going to get the idea. Okay, so the first colored in part was called stage 0. Now this is stage 1 where I've removed the shaded area from this equilateral triangle. Now I'm going to do the same thing again with the smaller triangles that I have. I'm going to go to the midpoint of each of those sides, draw a little triangle in, and then I'm going to remove the shaded area that's inside those triangles. So that's going to look something like this. Let's see, I'll go over here, do this one, and up here, and do this one. This is kind of messy, but you know, you could do this very artistically if you want, but you're going to get the idea. I just keep removing more and more area. That leaves me with a whole bunch more little equilateral triangles that are all shaded in, and so I'm going to go there to each one of those and remove that little center equilateral triangle and take the area that's enclosed by it out. So there I go, doing all those things. Okay, let's see if we can do this. So I remove that one, remove that, this one. Takes a little bit of time, but the first time through I think it's worth it so you can really see what's going on. There's no end to how many times I can do this, and really I'm doing the same thing every time. Now, if I keep doing this, I keep going, and each of these little triangles that I have, I go and mark on the midpoint of each of their sides, draw a little equilateral triangle, remove that area. I just keep doing that over and over again. I do that infinitely many times. The thing I end up with is called a fractal. And as a matter of fact, it has a specific name. It's called the Sierpinski triangle. And here's a picture of it in a little more detail. You can see that a lot more of the little triangles have been taken away. And you can imagine how this looks as you keep doing this an infinite number of times. Now, one interesting property that fractals have is a property called self-similarity. And self-similarity says this: if I take one complete piece of this triangle, it has all the information that's in the whole triangle itself. So if you can imagine that I've taken out more and more of those little triangles, this triangle right here, if I was to blow it up, would look just like the whole triangle. Same with this triangle down here, this little triangle here, so on and so forth. Each complete piece of the Sierpinski triangle has all the information in the whole piece, and that's called self-similarity. So look what happens when we zoom in on a piece of the Sierpinski triangle. It reproduces itself, whether we zoom in or whether we zoom back out. So you can see this idea of self-similarity is a pretty interesting idea. Now I want to show you a picture of a couple of other pretty famous fractals. First of all, the Mandelbrot set. I think you've probably seen that before, maybe, maybe not. Here's a picture of a fractal fern. You can see that fern looks a lot like just a regular fern that you might see walking around, and that's one of the reasons that people like to study fractals, because they think they sort of resemble the world around us. Now what I want to do, I'm going to erase this and I'm going to redraw the Sierpinski triangle here in its the first few stages and see if we can't relate it to what we've been doing with sequences. So I'll be right back. Okay, so I've drawn out the different stages of the Sierpinski triangle. Right here I'm calling this stage 1. Everything's colored in. Then I remove that center triangle, remove the center triangle from each of the little triangles that's left, and then continue to do that. So stage 0, stage 1, stage 2, stage 3. Let's suppose the area of the shaded region in stage 0 is 1. What's going to be the area of the shaded region here? It's going to be less, right? Because we have removed this equilateral triangle right here from the middle. Well, there's 4 equilateral triangles, only 3 of which are shaded, and so the area of the Sierpinski triangle at stage 1 is 3/4 if the original area right here is 1. What happens when we go down here? Well, we're going to have taken 3/4 of what we had to start with. Here's what we had to start with. We take 3/4 of that. We get 3/4 of 3/4, which is going to be 9/16. And then when I get down here, what do you think that's going to be? Well, that's going to be also, we're going to have 3/4 of the area left of the area that we started with. Well, this is what we started with, so we're going to have 3/4 of that. So 3/4 times 3/4 times 3/4, that's going to end up to be 27, all divided by 64. So what happens as we remove more and more of these triangles? Well, intuitively, you know, and also mathematically, you can figure it out too, because this this sequence right here, the numbers in this sequence keep getting smaller and smaller. 27 over 64 is less than 9 over 16. The one after that's going to be less than that. Every time I multiply by 3/4, I get a number that's 3/4 as large as the one before it. What happens? That area goes towards 0. Which makes sense because the more and more of this we remove, the less and less area we have. So when you think of this going out to infinity and the Sierpinski triangle being the end result of that, we end up with a geometric figure with 0 area. Now, look for a minute at the perimeter. Here's the perimeter in stage 0, the perimeter of the shaded region. What does it look like in stage 1? Well, it's my original perimeter here. Plus, now I've got this perimeter on the shaded region. So I've added a little more perimeter in stage 1. In stage 2, I've got this whole perimeter that I started with, plus this right here. Now I'm just going to outline the shaded region here and ask what the perimeter is. Well, it turns out that that perimeter is getting larger and larger. So I end up when this goes all the way out to infinity, the Sierpinski triangle, I end up with a geometric figure with infinite perimeter enclosing 0 area. Kind of an interesting thought. So there's a lot of interesting things that go with fractals. This is probably the simplest fractal that we have. Look at this area here, convince yourself that it goes to 0, and then think about the perimeter of that shaded region, and you'll see that that's getting larger and larger. As a matter of fact, it's getting infinitely large. So if you're watching this on YouTube, there's plenty of other videos on YouTube about fractals. Do a search for fractal zoom, fractal landscape, or just plain fractals, and you'll see all kinds of models of maybe the Sierpinski triangle, Mandelbrot set, maybe even that nice fractal fern. So I hope you enjoyed this.